All right, let's talk about LeetCode 1980. Find unique binary string. So we're given an array of strings nums containing n unique binary strings, each of length n, and we want to return a binary string of length n that does not appear in nums. If there are multiple answers, we can return any. So kind of a couple key things to note before we get started. N is the length of the list, but it's also the length of the strings. So that kind of simplifies it. We don't have to keep track of a bunch of different lengths. It's all the same. And then the other thing is we can return any permutation as long as it's not in nums. So we don't have to find any kind of specific target. We just have to find one that they don't already have in the list. So I'm not going to draw this one because I don't think it would help much. I'm just going to go straight to coding it. Kind of the first approach I took to this one was to use backtracking. So we'll do vector string perms and just use backtracking to generate all the permutations. So vector string perms, just for housekeeping, I'm going to get the n from nums.size just because I feel like we'll reuse that a lot. You don't have to. You could just call nums.size every time you want to use it, but I'm going to do this just for cleanliness. Let's say n equals nums.size. And then we'll have to have a method to get all the permutation. So we'll say get perms. And we'll call that here. Get perms. We'll have to pass it perms to add the permutations we find to the list so we can use them later. We'll need n because we'll have to use that for base cases to stop the recursion once we get to the target depth. So we'll say n, or just n here. And then we'll need a builder string for the intermediate steps that we can add digits to one by one. So let's just implement. So we'll say vector string perms, and this needs to be by reference so that we can use the permutations we find when we get back here. In C++, you can use an ampersand to pass by reference. Hit n, and then we'll say string cur for current. Okay, so since backtracking is recursive, let's think about our base case here. Well, we don't have any base cases. We're just going to build a string of infinite length. We'll just keep adding a digit and going deeper and deeper and deeper into the recursive tree until eventually we just run out of memory and the whole thing crashes. So where do we want to stop? Well, we only really care about strings that are of length n. So that's a good stopping spot. If cur.length equals n, well, if cur.length equals n, then it's a valid permutation for what we're looking for. So we can add it to the permutation list. We'll say perms.pushback cur. And then we also don't need to go any deeper because any deeper we go into the recursion tree, there's going to be too many digits in the string anyway, so it's not going to be valid. So we'll just return. And then if it's not the base case, then we do our recursive step. So we say for I equals 0, I is less than 2, I plus plus. And where the 2 comes from is we're dealing with binary here. So 0 and 1 are the only two valid values. So we just stop at 2 so that it breaks. And we get all the permutations that start with 0 and then recursively go down and test all the combinations past there for each digit. And then we come back and then we go to 1. We get all the permutations that start with 1 and then recursively test each digit from there to get all the combinations. And then we get back, it goes to 2 and breaks the loop, and then we go back to the parent method. So within here, we do cur plus equals. We need to convert to string because we're dealing with strings. So we add a digit to the current string, and then we need to go a step deeper in the recursive tree to see what the next possible combinations of digits following this digit are going to be. So we'll do get perms. We can use the same values, so perms in, and then the updated cur. So we go one step deeper. Now when that gets back, now we get this cur, but we have an extra digit because we added a digit to go to the next level. So we need to take it back off so that we keep the cur corresponding to the level we're on in the recursion tree. So cur.popback. So this just removes the last index, which will be the one we just added. So I think that's good. Now, the only thing about this is this generates all permutations, which is kind of wasteful for our use case because we only need one. We don't need all the permutations. We just need one that they don't already have. So what we can do is we can add an extra base case here to save ourselves a little bit of time. If perms.size is greater than n, So as soon as perms.size is at least 1 bigger than n, that means there's at least one permutation in that list that isn't in nums, because there's one more element in perms than there is in nums. So we have a guaranteed valid return. So we don't need to generate any more permutations. We don't need to go any deeper. We can just return. We have what we need. Okay, I think we're good here. Yep. So once we get out of here and all this has run its course, now we get back to here and we have this perms list with one extra permutation, which will be our return. So now we just need to find it. So we can do for I, if I can type 0, I is less than perms.size. So we'll look at each permutation within the perms list. I don't know why. Okay. And then for each one of those permutations, we need to check and see if it's already in nums, because if it is, it's not a valid return. So int j equals 0, j is less than, and there's better ways to probably do this than a nested loop, but I'm going to show you another solution, so I'm just going to do it this way for simplicity. Nums.size, j++. So we'll iterate over, and then I'm going to add a marker called int scene, or bool scene, false. And if nums at j equals perms I, well, if the two strings are equal to each other, then that means that the permutation we're looking at in perms is already in nums, so it's not a valid return. So we'll say scene equals true, and actually let's do it this way, just for a little bit of extra optimization. Not much. Break. We'll break after, that way we don't have to keep going, because if it's already been seen, then we know it's there. We don't have to look at the other ones. Okay, so once we hit this break, or this just runs its course, we break out of this inner loop. Now, if not seen, so if seen is still false, then that means that the string that we're looking at in perms was not in nums. So we have a valid return. So we just return the current index. Perms. And then because we're doing our return within this conditional, we have to give it like a default return. Otherwise, we're going to get an error. So we'll just do return of empty string. But we're never going to get here. And then we should be good. Unless I made a dumb typo somewhere, which is likely. Let's give that a shot. See what we get. Yeah. So we're good. Let's see how that does. So not bad, not good either. It works, but it's pretty slow and kind of uses a lot of memory. But if we think about the problem, there's actually a way simpler way to do this. I mean, this solution, we're looking at like 2 to the n here because we're dealing with binary. So the permutation thing's pretty slow. And then we have this nested for loop. So this would be like n plus 1 times n. So probably kind of simplify to n squared. It's just not really optimized code. But because this problem has this kind of simple n that just occurs over and over again, and we know that for each unique digit in our return string, there will be a unique string in the nums list, we can kind of guarantee that we get a unique string without having to generate any permutations. And the way we do that is we can do something like this. We can do for int I 0, I is less than nums.size, and I plus plus. And the cool thing here is we don't have to do a bunch of nested loops because everything is linked in. So we can reuse I to represent multiple things. I'm going to do string ret for return. It's just an empty string. Okay, so all we have to do is say if nums I equals 1, and this should be a char because we're indexing a string. Then ret plus equals 0. And I'll explain in just a second. else, because we're doing binary, it's only ever going to be a 1 or a 0. Ret plus equals 0. And then once we break out of the loop, we just return ret. Let's try that. Uh-oh, I typed something wrong here. I0 has less numbers outside, I plus plus 1. Oh, duh. Sorry. 1. Yeah, there we go. So if we submit this, and you see that's way faster. And we used a lot less memory. So we're doing this in linear time. And the way this works is we go through and we say, okay, we have this list. So so for the ith index in the list, so this 111, we want to look at the ith digit, so this one, and we want to put the opposite. So this is a 1, so we'll put a 0. And then we go to the next index in the next iteration. So now we're here, and now we're looking at the first index. Remember, strings are 0 index just like this, so we're looking at this one. And if it's a 1, then we put a 0. So currently we have 0, 0. And then we go to the last one, and then we're looking at the last index. And if it's a 1, we put a 0. So we would get 0, 0, 0. And we're guaranteed to get a string that isn't in the list because we're going digit to digit and we're going index to index. So all of these are not going to match because this one is going to have at least one digit that's wrong because we got it directly from here. This one's going to have at least one digit in the second place that's wrong. This one's going to have at least one digit in their third place. This only works because the list is the same length as the strings, but you can kind of hack this problem and do this, and it's pretty quick. But yeah,